let's level set with what are you going to learn today. So I think this session is for two kinds of developers. So the first one is for folks that are just beginning their AI journey. They might not have an application built, or they just might be wondering like, hey, this AI stuff seems interesting. How can I get started with Postgres? For you today, what I want you to walk away from the session with is an understanding of what kind of AI applications you can build with Postgres. And you're going to learn enough to get started building straight after the session. You're going to learn enough to build like an MVP or some sort of toy application in after this hour. So that's what you're going to learn. And then for intermediate folks, for folks who already have an AI application or maybe the basics, maybe you already use Pgvector or something like that, what I want you to walk away from the session from is tactics and ideas for you to improve your AI application. No matter if you're just starting off or if you already have an application, even in production, you're going to learn from the session, and it's going to be jam-packed with value. With that in mind, let's take a look at what we're actually going to cover in today's session. We're going to split the session into 4 parts. The first one is going to be about foundations. This is, again, for folks that are completely new. We'll talk you through what kind of applications you can build, the extensions that you should use to build AI applications with Postgres, and we'll do a small demo building a RAG and such application from scratch, just using SQL. Then we're going to get into some of the more advanced stuff. I'm going to take you through vector search indexes. In Postgres, we're going to look at the differences between them and which one you should use and when. That's always an interesting topic. And then number 3, this is for the intermediate and advanced folks, improving your AI system. We're going to look at things like evals-driven development, filtered search, hybrid search, multi-tenancy, text to SQL, and give you a taste for how you can take your system to the next level. And last, but definitely not least, we'll leave 10-15 minutes at the end for Q&A for you to get your questions answered. We can move on to the first topic, which is about foundations for building AI systems with Postgres. Okay, so this is going to be a recap for folks who are intermediate and advanced. So just give me like 5-10 minutes, and then we're going to get into stuff for you. But for folks who are beginners, the main thing I want you to take away from the session is that you can build AI applications with Postgres. You don't need a team of researchers in order to build something state of the art. And you also don't need a specialized database or something new if you already know and love Postgres. So let's unpack the statement a little bit in order to see what I'm talking about. When I say you can build AI applications with Postgres, if you're in this live session, you're probably one of these sorts of developers or engineers. Maybe you're a software engineer, maybe you're a DBA, a data engineer, an AI engineer, but you're likely an application developer without a specialized AI or ML background. And the point of today's session is to show you, with the advances in LLMs and off-the-shelf technologies, that you can build an AI application with Postgres just having this background. And that's because what I like to call the rise of the AI engineer, the rise of this application developer who uses AI to build products rather than a researcher or a research scientist that is actually like building the models themselves. So this is a graph that I've taken from a great blog post from a guy called 𝗥𝗲𝗃. You can see the link over here. But basically the idea is that you don't need to be an ML researcher, a data scientist, a research engineer. You can have that background, but you're more likely a full stack engineer or what I'm calling this new breed of engineers, an AI engineer, someone who uses AI to build useful products that users actually use. That's the first thing as a mindset for you to have, that, hey, just using the skills that you have, using the database that you know, you can build an AI application. You don't need a PhD in ML in order to build an AI application. The next thing that we're going to do in the foundation section is take a look at how Postgres fits in, starting with the concept of a vector database, a term that you've probably heard a lot about when it comes to building applications with AI and LLMs. So what I'm about to do is a very short, very non-comprehensive crash course on what is a vector database. And if you already know this, again, this is going to be a review for you. But if you're brand new, this is the key things to take away. You can obviously learn more by reading some of the articles that I'm going to recommend. Okay, so let's start with, before we get into a vector database, what is vector data? Vector data is essentially compressed representations of data. So the key thing here is that you can have different kinds of data types. Let's say you have an image, you have a document, you have maybe even audio. And what a vector is that it is a compressed representation of that image or document or audio. and you create vectors from these embedding models, which take in things like images, and then they output essentially a array of numbers or a list of floats, however you'd like to call it, that represent that image or the meaning of that image or document or phrase in multi-dimensional, like high-dimensional space. So that's all you have to know. What is a vector? It's literally a list of numbers. That's what you need to keep in mind. And they're essentially compressed representations of different data types that you're interested in. And so a vector database, simply put, is just a system that stores and searches vectors very efficiently. And the key idea here, why is a vector database useful? Because of the rise in LLMs, and I know there's other applications that we're going to get to in a moment, but you're probably here because you want to build an AI application that uses LLMs. And one of the key insights that we saw after the explosion of ChatGPT is that vector databases allow LLMs to work with your data. You can actually, through a process called retrieval augmented generation or RAG, fetch relevant context from your vector database and pass it to an LLM to then do reasoning and compose answers on. And a lot of the key ideas is, hey, what if you could combine ChatGPT with your documentation? What if you could combine it with your blog posts so that your users can answer questions? What if you could add it to your documents in Google Drive or something in order to get shared context across your company? This is the kind of motivation for all of this. Again, very simply put, like where does a vector database fit in? It essentially connects LLMs with your data. Okay, so now that you know a little bit, at least what is a vector database, what is vector data, let's look at the types of applications that you can build using Postgres. What can you build using Postgres in terms of AI systems? So the first one is RAG. You can think of RAG as, like I mentioned before, ChatGPT, but with your company or customer data. And examples of RAG applications are things like you've probably seen in your Twitter feed or LinkedIn feed, customer support chatbots, research copilots, docs chatbots, anything where you want to chat with some sort of specialized context in mind. This is what's called a RAG application. There's also another type of application called a search application, which is mostly semantic search or image search. And that is you want to search and find information, not necessarily by keyword or tag, but by meaning, by kind of the underlying meaning of the artifact, whether it's image, whether it's a sentence or something like that. Getting into some of the more advanced stuff, you have agents. So agents is essentially, if you haven't heard of an agent before, it's ChatGPT that can use things like tools. It can plan, it can take autonomous actions. And some of these tools might be the ability to do web search, the ability to query a database, the ability to use APIs, make API calls, etc. And I'm sure that some popular examples of this, the AI software engineer products out there that you might have seen, things like Devon, things like Rapid Agents. This is an example. Then we even get some even more advanced. And this is a good thing about Postgres, the fact that it's a relational database. You can do things like text to SQL, where you can imagine it's like ChatGPT, but for your numerical, structured, and tabular data. And so here it enables things like asking questions in English versus writing formula code. And you'll see some examples of this out there. Chat with your data applications, data and financial analysis agents. These are some examples. And there's also more things you can do. I've just put 4 big topics that I've seen, but there's also, you can build recommendation systems, you can build anomaly detection. There's so many applications of vector databases and Postgres in terms of building AI systems. And for example, if you're doing like time series anomaly detection, or you're trying to build an e-commerce purchase recommendations feature, you can power this using the vector database functionality inside Postgres. Okay. You now understand what you can build. You understand what is a vector database. Let's get a bit more concrete and look at the most popular Postgres extensions for dealing with AI and vector data. To level set for folks who might not have heard of Postgres extensions, but basically the power of Postgres is that you can use extensions to turn Postgres into and give it like specialized capabilities without sacrificing its core relational database capabilities. Many of you here at Timescale, you might have known TimescaleDB, which is an extension for time series. And if you add Postgres with the TimescaleDB extension, you turn Postgres into a time series database. And then in the same way, if you add these extensions that I'm going to talk about, Pgvector and pgAI, you turn Postgres and you give it the capabilities of a fully fledged, all you need vector database. And so this idea of extensions is very important because that's how we actually get vector capabilities into Postgres. Okay, so now that we've established what extensions are, let's look at the top 3 Postgres extensions for AI applications in Postgres. We'll start with Pgvector. This is probably the number 1 extension you need to know for building AI applications with Postgres. Pgvector essentially gives Postgres vector database superpowers. It has capabilities for a vector data type as well as distance functions. So you can see there's the distance functions that are supported here, cosine, L1, L2, inner product, etc. And it also has some vector search indices built in, which I'm going to take you through later in this presentation, but there's 2 of them, HNSW, IVF flat. Now, the cool thing is about Postgres is that extensions can work together. And so what we have is more extensions that actually build on top of Pgvector in order to augment it and extend it for even more capabilities. So one such extension is Pgvector scale, which actually speeds up Pgvector for large-scale workloads. So this is a complement to Pgvector, meaning that you can use them together. And it allows you to do things like high accuracy filtered search. And it also comes with its own vector search index that you can use with Pgvector data called streaming disk NN. And then finally, we have pgAI, which is a bit different in the sense that it brings AI workflows to Postgres. It allows you to do things like embedding creation and do in-database LLM reasoning. So if you want to do things like create summaries, maybe do moderation, maybe do categorization, you can use it with the pgAI extension. And the cool thing about all of these is that they're open source. So you can use them for free. You can download them. You can install them on your Postgres database. It's supported on most cloud providers. We support all 3 of these extensions in the Timescale cloud platform. And now that you know what these are, let's look at how you can use them. And I know there's a question in the chat from Jean-Michel who says, hey, can you use these extensions at the same time? Not only can you use these extensions at the same time, but they actually depend on each other. So for example, here's a create extension statement for installing these 3 extensions in Postgres. But if you install the AI extension or the vector scale extension, it actually automatically installs Pgvector because it's actually a dependency. So these extensions really work closely together, and you can and you should use them together. Okay, one of the key takeaways, just to wrap up this particular section, is that Postgres is all you need to create AI applications. This is a market map that I found online of 50 different vector database products, vector libraries, etc. And I love memes. This is a Drake meme. You don't really need any of these specialized systems to build AI applications. If you already know how to use Postgres, if your company already uses Postgres, all you need is just Postgres to do this. And you can see here another example. Postgres, in addition to its relational database capabilities, can become a high-performance vector database thanks to the extensions that we've talked about. Before we move on, I wanted to give you some reasons for if you had to think about why Postgres is beneficial for AI applications. There's kind of 5 reasons to think about. So the first one is you can have one database for your AI application. You don't have the complexity of managing a separate vector database and dealing with things like data synchronization, data duplication. You just have one source of truth, and that's super valuable, especially for us who worked on more complex applications. Some of the other benefits is that you can store vectors alongside vectors and alongside metadata. So you store your vectors alongside your metadata and your other application data, even things like time series, geospatial data. And not only is this simpler, but it actually facilitates more powerful user-facing features that we're going to see in part 2 and 3 of today's presentation in the filtering section. And then the third point is that Postgres can actually perform and scale as well, and sometimes even better than a specialized vector database. This is a graph that compares Postgres to Pinecone. And you can see the P95 query latency is a lot lower. It's 62 milliseconds. What that means is that 95% of queries that we ran on this 50 million vector dataset were below that 62 millisecond cutoff. And you're not actually going to give up any performance or any scalability by using Postgres versus something more specialized. And then you have all the good things that we know and love: reliability, ecosystem, SQL query language. And one of the other cool things is that you can go beyond simple vector search for your application. So you can do things like hybrid search, filtering, text to SQL. We're going to get into all of these later in the presentation, but this is all possible with the fact that you have vectors and other kinds of data all in one SQL table or all in the same system. Okay, so now that we have finished the first part of today's presentation, we're going to take a break from the slides and we're going to look at a demo. What we're going to look at in today's demo is an example of using Pgvector and pgAI for a RAG use case. Okay, so Let me know if you can't see my screen, but everyone should be able to see this. This is Popsicle, and you can see here I'm connected to a Postgres database. And so all of this, while this is a UI, this is not a specialized application. All of this is happening in the database layer. And you can see on the screen here, I have a table. So I have this quotes table, and you can see here that it's quotes from various historical figures throughout history, people like John F. Kennedy, Mark Twain, Truman Capote, and they're about different cities in the USA. So let's examine some of them. This is Truman Capote about New York City. And you can see I have a quote, I have the person, and I also have this embedding column. And this is the cool thing about using Pgvector and using Postgres is that you can store embeddings alongside your relational data. But you'll notice there's a problem here. I don't have any embeddings. So the first thing that we're going to do in this demo is create some embeddings for all the quotes in this table. So let's take a look at, just for folks who want to understand a bit more, this is the create table statement for the quotes table. And you can see here when I'm creating the table, the vector is just a data type. So I have this, I'm naming this column embedding, and I just have a vector data type, and I specify this 1536 as the dimension of the vector. And this data type is coming from the Pgvector extension. So you can see here, you don't need to do anything crazy. You just specify your vector column and you give it the dimension that you have, and you'll know the dimension from your embedding model that you're going to be using. And skipping that, you've seen that you can store vectors alongside relational data. What I'm going to do is use the pgAI extension in order to create embeddings for all of the quotes in this table. So what I'm going to do here is run this particular command. And what's happening in the background is we're using OpenAI's text embedding 3 small model to create embeddings for all of the quotes in the table. And this OpenAI embed function is part of the pgAI extension, which we talked about earlier in the extension section of the presentation. Now that's run, let me do a quick select star from the quotes table, and let's see what happened. So we can see here that just by running that query, we've created a whole bunch of embeddings for the data in our table. So let's take a look at one of them. You can see embedding, once again, just a long list of numbers. And this embedding represents this particular quote that came in. And now that we have embeddings, that allows us to do cool things like search and RAG that I talked about. So let's look at an example of that. And once again, this is a cool thing about the pgAI extension. You can just create embeddings in SQL. You don't have to run a separate data pipeline, especially for these small to medium examples that we're looking at. So let's look at an example of 𝗔𝗯𝗃_𝗁 where what I'm going to do is try to find quotes in my table that are similar to this phrase called empire state of mind. But again, when you're doing these vector searches in Postgres, it's the same select query. I want the ID, the quote, the person who said it, and I want to order by the embedding that's most similar to the embedding that got generated from this particular phrase over here. So this is, once again, an easy way to create embeddings in order to do such. And then this is the only new thing when you're writing your SQL query. So let's run this and see what gets generated. And you can see here what I'm doing is I'm fetching the top 3 quotes that are most relevant. And you can notice that the top quotes that I have are about New York City. So you can see here, New York, even this quote also has New York, even though I don't have New York in my query as well. I query for empire, state of mind, etc. But because these two phrases are semantically similar, this is how we get this kind of results. That illustrates the value of semantic search, but you can go beyond search and do things like RAG, which is what I'm going to show you next. And then also just to note, I wrote the SQL query just to show you guys, but you can actually encapsulate these in functions and then just call the function to make it easier. So for example, let me just run this. I can't remember if I've done it. Let's just encapsulate it in the function. So we ran this. And then instead of writing that whole SQL query out, whenever you want to reference it, you can just reference this function and you can run this function and you'll get the same results in a moment. And it'll show you what the results that you've gotten. Okay, if you want the similarity score, there's a place in the Pgvector docs that shows you how to get that. For the sake of real estate on the screen, I'm not showing you today, but there is a way to get that, and you can do that in order to get the actual raw scores if you want as well. Okay, so next what we're going to do is we're going to do some LLM reasoning over the quotes table that we have. So let's say, for example, what I've just showed you is doing a similarity search. But what if I want to have some sort of batch operation where I'm like, hey, from the quotes in this table, I want to know what people say about the various cities. So in this case, I'm going to use this function called generate RAG response, which I'm going to take you through in a moment. It's a function that I've made in order to do RAG. And what that means is fetching the most similar quotes and then processing it in an LLM in order to figure out what does my quotes database say about these cities. So let me run this. And then while that's running, let me take you through that function. Okay, so let's take a look at this generate RAG response function. What does it do? The first thing that it does is perform a similarity search in order to find the relevant quotes. So in this case, I'm just finding the top 3 quotes, and I'm going to pass that to the LLM. In this case, I'm using GPT-4o Mini, not ChatGPT, GPT-4o Mini. And what you can see here is this is the base prompt that you can customize, the system prompt. And then you can also customize what things you're passing. In this case, I'm passing the chunks that I've just created from the similarity search as the context, and then I'll get a response. So that's what's happening in the background when we're doing all of this. And let's see what our answers that we got are. Just delete this. I have this stored in a table called summaries. And here we go. So we can see for each of the questions that I asked, what do people say about New York, San Francisco, Chicago? I now have summaries. And in my particular prompt, I asked it to say, hey, instead of just summarizing, tell me the exact quote that people say and give me the sentiment. And here's an example. And you can see the exact quotes being displayed over here by GPT-4o. Now, you can easily see this is such a simple toy example, but you can easily see this can be used for things like, for example, building a customer call application, building a call recording application, anything where you need quotes, where you need to summarize what people have said. This is how you can do it. And this is just a simple example of how you can do it using the pgAI extension. Okay. Hopefully that was interesting if folks haven't seen the pgAI extension in action and also haven't maybe even used Pgvector. That was like an introduction to it. Okay, we're going to go into the second part of this session today, which is vector search indices. Someone asked earlier, what is the drawbacks of pgvector scale versus Pgvector? This is where we're going to answer that question. And it's really the pros and cons and when to use which. We're going to learn the answers to that in just a moment. Let's take a step back and ask, why do you even need a vector index in the first place? Maybe you've heard of this term before, but if you haven't, this is why you need a vector index. Really, what happens is that when you're dealing with a lot of vectors, you encounter something called the curse of dimensionality. And so what you do is that you then perform what's called an approximate search or approximate nearest neighbor search, where you trade off some accuracy for faster search speeds, and you use approximate algorithms in order to do that. And the question is, this sounds really cool, but like how many vectors do I need in order to use search indices? We'd recommend from our experience somewhere around 100,000. You can actually get away with just doing what's known as brute force KNN search or exact nearest neighbor search on anything less than 100,000 vectors most of the time. Obviously, if things are slow, then use a vector index, but you don't need to use it from the start if you are dealing with a small number of vectors. And the good news is that we have 3 vector search indices in Postgres in order to use. And they all have different pros and cons, but just to introduce them before we go into it, there's the IVF flat index or inverted file flat. That's what it stands for. There's HNSW index, which stands for hierarchical navigable small words. And there's a streaming disk NN index, which that's what it stands for. There's no abbreviations going in there. The ANN stands for approximate nearest neighbor search. But the names are an indication of the type of vectors they are. So this is an inverted file vector search index. This is actually a graph-based index with a multi-layered graph. And then this streaming disk NN index is also a graph-based index, but it's a single-layered graph for those of you who are interested in those kinds of details. But if you just want to know when should I use which kind of vector, I don't really care how it works. I just want to know when should I use which one and what are the pros and cons. This is the slide for you. This is the screenshotable slide where I take you through these 3 kinds of indices. You probably have questions about when do you use which of each index. And so let's start with IVF flat. This was the first index that was introduced in Pgvector. It's good at medium workloads. Again, it's faster than a linear scan, and it does have the pro of low memory usage, but it does have significant drawbacks. The main one is that you have to rebuild the index every time you update the vectors in your table. So if you have dynamic data, if you have a lot of updates or deletes or inserts, this is not a good index to use because you're going to have to spend your time updating, rebuilding the index. It also has lower accuracy than other index types like HNSW and streaming disk NN. So in general, if you want to use IVF flat, go ahead, but we recommend using either HNSW or streaming disk NN index for most use cases. Okay, next, let's look at HNSW, which is actually a very popular kind of index. Other vector databases have it as well. This is a good kind of all-round index. It's good enough for real-time search on what I'm calling medium workloads, so 100K to 1 million vectors, maybe even 10 million vectors if your vectors have small enough dimension. And it has a lot of good things about it. There's a good balance between search speed and accuracy. It can handle updates without having to rebuild the index, so that solves the con in IVF flat. It has options for quantization, which is essentially vector compression, and it also has a pretty fast index build time and some index, the ability to parallel or to parallelize the index build process, if I remember correctly. But it does have its cons. It has known problems, and this is something that we've seen with filtered search accuracy because of the way that the search mechanism works. Some of the other drawbacks about it, in addition to the filtered search accuracy, is that it has high memory usage. Vectors have to stay in memory the whole time. The vector index has to stay in memory the whole time. And as a result, your costs scale with your RAM. And as we know, RAM is pretty expensive. So if you need more RAM, you need to go to the next level in your cloud provider. And that does, unfortunately, cost a bit more as you scale up the number of vectors that you have. And then there's also scale limitations in terms of search speed and accuracy from the tests that we've done and what we've heard from users. As you get to a large number of vectors, you can have things slow down or reduce accuracy. And that's where the streaming disk NN index comes in. And this is what's in Pgvector. What it's good for is, once again, real-time search, just like HNSW, but it really excels in these filtered search use cases where in a moment, I'm going to tell you about the different kinds of filters, but where you don't just want simple semantic search, but when you want to filter on things like metadata or some other attribute. And it excels at large-scale workloads. So the example that I showed you earlier was on 50 million vectors. Anything over 10 million plus, I'd recommend using streaming disk NN. That's going to give you the best, most worry-free experience. Some of the advantages of streaming disk NN is the super high accuracy for filtered search, as I mentioned. You can scale to more than 1 billion vectors. It also has quantization on by default, and it's a specific kind of quantization that we built at Timescale called statistical binary quantization. But one of the cool things for those folks who are maybe thinking about production and thinking about costs is that the costs actually scale with your disk and your RAM and not just your RAM itself. And so what that means is that you don't have to automatically update to the next tier of memory. And even if you, because of the fact that the way the disk is stored, you can leverage SSDs in order to store the index without sacrificing search speed significantly. And then another pro is that you can handle updates without rebuild, just like HNSW, and so that solves this problem in IVF flat. The one con that we found, that just to be balanced, I wanted to share, is that you do have longer build times than the HNSW index in this case. Usually, this is only a problem when you're starting off. You build the index once and then it will update itself as your data changes. But this is something that we've noticed. If you're trying to load a large number of vectors very quickly, you're going to have to wait a little while. And that is a known limitation that we do have some plans to address. Okay. You can send this to your team when they ask, what is the difference between all these different vector indices? Hopefully that gives you a good overview of the different indices. Okay, so how do you use vector search indices in Postgres? The good news is that you use it just like all the other indices in Postgres. You just run a create index statement. And this is an example of how to create all 3 indices. Just a note that you can't have multiple index types on the same column. So you can see over here, that over here, I'm creating it on the quotes column, and I'm using that in all 3 examples. You would just use one of these on the quotes column, but you can have, say, for example, if I had like quotes 2 and quotes 3, and I wanted to compare the index types, I could do that in separate tables or in the same table. But in the same column, you can't have more than one index. But this is an example of how you can create IVF flat indices. And over here, just note that you have to specify the kind of distance function. And so we're using cosine here, but there's also other ones. You can see the specific distance function in Pgvector documentation. And here's how you create the HNSW index. And then last but not least, the streaming disk NN index, which is just known as disk NN in the code. And so that's how you created 2 lines, and then you're up and running after the index builds. And then the good thing about Pgvector and kind of Postgres in general is that if you want to get in the weeds with things like index configurations, you have full control over the parameters. It's not like other systems where you just set it and then when things go wrong, you're like, okay, I have no knobs and dials at my disposal in order to debug and try and fix these things. So each kind of index type, there's different configurations that you can use. And all of this is in the Pgvector documentation, the Pgvector scale documentation. I'm not going to go through each parameter right now, but just know that for the folks who are advanced, they can look at these different settings. And if you are having trouble where the defaults are not working, you can actually change these and experiment with what works well with your use case. Okay, so where can you learn more? The good news is that we have 3 blogs on the Timescale blog that talk about these 3 different kinds of indices, one about IVF flat, one about HNSW, and this one is about the streaming disk-NN index, which we really compare to Pinecone to show how you don't need a specialized vector database. Okay, we're going to get into our last and most advanced section in a moment about improving your AI systems. And we're going to deal with some of the more intermediate and advanced topics. So if you're someone who you're like, hey, I already knew all the stuff, this next part is for you. And if you're someone who found all this other stuff interesting, get ready because you're about to learn a whole lot more and go more advanced than many people who maybe have even been building AI systems, because you're going to learn what I've learned from Timescale customers and other users and get a head start. Okay, so part 3, the final part of today's presentation, which is about improving your AI system. What are we going to talk about? We're going to talk about advanced topics. So this is beyond the 101 tutorials, beyond the build a RAG app in 10 lines of code. This is really where the useful stuff for users comes in. I'm hoping you're going to get a lot of value from this presentation because you're going to have all these tools in your toolkit and actually build useful AI applications that make it out of the MVP and POC stage. We're going to cover 5 topics. The first one is about evaluation-driven development. This is a mindset and a way of developing that I think is going to help you so much build useful AI applications. The next things we're going to look at are techniques in Postgres in order to get more accurate results and more useful results. So we're going to look at filtered search, which is essentially combining vector similarity search with filters or where clauses. We'll take a look at 5 examples. Next, we're going to look at hybrid search, which is combining keyword and vector search. Then we're going to comment a little bit on multi-tenancy for RAG applications. This is a super common concern. And then finally, we're going to look at text-to-SQL, just touch on it a little bit and talk about how you can leverage it with RAG and agents with tool use. And so this is really advanced stuff. Buckle in, pay attention. If you're multitasking, this is a good time to stop. Okay, so evaluation-driven development. What does that mean? So a lot of the times people start with AI applications like, hey, I might have an application in mind. Let me go and look at a tutorial and find some way of building it. What I'd actually recommend is this, or what I call evaluation-driven development. I learned this from a friend of mine. His name is Jason Liu. He's an AI engineering consultant. And basically what this is a system for making sure that you're actually building useful applications. And it allows you to measure, is your application getting worse or better over time? So the first step of this is actually to start with the set of questions you want to answer. So don't start by writing code. Start by writing down 10 questions that you think your users are going to want to answer and put them in a file somewhere, put them in a text file or something like that. This then becomes what's called your evaluation set. This is how you measure whether your application is improving or declining. And as I just said there, getting ahead of myself, as you make changes to the system, you can now measure if your app is getting better or worse. So for example, what changes might you want to make? Maybe you're using a new embedding model. Maybe you're upgrading from GPT 4.0 to 0.1. Maybe you're transferring from GPT 4 to Claude Sonnet 3.5. You want to know the differences that it's making in your application. You now have a way to test and to show other people, is your application getting worse or better before you hear about it from your users. And then also, the cool thing is that as your application gets more complex, you can just add more things to your evaluation set to make sure that you're picking up for these scenarios in the future. So maybe you'll start off with 10 queries, but you'll eventually grow to 20, 30, 40, 50 questions, and you'll have different sets where you can say that your application gets better or worse. The final thing about evaluation-driven development is to actually decompose the problem. So a lot of the time in LLM applications, we just focus on the answers that LLMs give us. Oh, this is the output that I got from ChatGPT. It doesn't look right. The ChatGPT must be silly. AI sucks. That's not the case. If you decompose the problem into smaller steps to actually understand, okay, what's going on under the hood. So for example, here's 3 examples of how I'd apply decomposition. The first one is in RAG applications. Let's first see, are we actually fetching the right chunks or right documents? Do we have an inventory problem where users are actually asking questions and we don't even have these documents that are related to it? So of course, ChatGPT is going to be giving bad answers, or the LM is going to be giving bad answers. The second thing is in the agents example, agents can use a lot of different tools. Uh, are you actually selecting the right tools to use? Are you using a database query tool when the user asks about analytical things? Are you using a semantic search tool when the user asks about things in your knowledge base, etc.? So start with things like that just to see what's going on, get a trace of what's going on in the system. And then, for example, in text-to-SQL, are you actually querying the right tables? Is the table forget about the SQL syntax, are you querying the table that has the answers to the stuff? And then you can focus on things like, hey, getting the right SQL syntax, etc. There's a blog that I'll recommend at the end called RAG is More Than Vector Search. We just put it out last week. I highly recommend to read it. You'll get a good sense of this mindset. But basically, I wanted to talk about this first because this is the mindset that's going to help you build useful AI applications and stop you from wondering what's going on. If you follow this, you'll actually build useful things for your users and you'll get a promotion and you'll be a lot happier because you're actually building useful stuff. Okay, so that rant out the way, let's look at the first thing that you can do in order to improve your AI application, which is filtered vector search. If you're building an AI application, why do you want to add filters? You want to add filters in order to get better search results. So instead of doing just like pure semantic search that we just saw in the example earlier today, you'd want to maybe filter on different attributes so that the search space is constrained and that your users can get more relevant results returned to them, or that your RAG has more relevant results. So let's take a look at 5 examples really quickly. So the first example of filtered search is a metadata filter. This example, so again, I have these code examples on the screen. You'll get a file with all of these later. The first example is a metadata filter, and here you can see the use case that I thought of is, hey, you maybe have a documentation search system and you have multiple products. So here you can see we're not just selecting and ordering by the cosine distance, but we're doing a clause that like filters, hey, I want the CRM software product and I only want API reference docs. This is how you can implement this from the backend perspective. The key thing here is this ability, again, keeping vectors and metadata in the same table, and it's super easy to filter. It's just a where clause. And once again, this is a real world use case, in this case, like technical documentation search, where you have multiple products. So that's a metadata filter. The next kind of filter is what I call a composite filter. So this use case is an e-commerce product recommendation system that considers a bunch of things before you recommend the product. So for example, let's say in this case, we're not just selecting the product and like the cosine distance to, let's say, the current product that the user is looking at. In this case, we're not just looking at the product, the vector search, but we're doing a whole bunch of filtering to say, hey, this product needs to be in electronics. This product needs to be between $500 and $2,000. It needs to be in stock. You don't want to recommend things that are out of stock, etc. And it needs to have a minimum rating, etc. So this is, again, the power of SQL, the power of Postgres. It's so easy to write these kinds of queries in Postgres and Pgvector. And that's an example of a composite filter. And then the third kind of filter is a time-based filter. So this example, I have a news article recommendation system that retrieves semantically similar articles that are published in the last 7 days. And this makes sense. You don't want to read old news. It's called the news because it's new. And so you want to give your users recent articles. This is a classic example of where filtering by time makes a lot of sense. And again, you can actually combine the beauty of Postgres extensions, combine this with TimescaleDB hypertables for those of you who use the TimescaleDB extension to get efficient time-based search if you have a lot of time-based data already. So again, this is really simple. We just have a where clause once again. Then another example is a permissions-based filter where this is super common in RAG applications where different users, especially internal apps, where different users have different levels of permission. So let's say the CEO has the most level of permission, but Avthar, who's just like a normal guy, he has the lowest level of permission. So you do want him to access all the classified documents. So this is how you can implement that, for example, in a semantic search where, when a certain user searches for documents, it ensures they only use documents that match or are below the user permission level. And so this is an example of how you can do that. Once again, in SQL, this is super simple. We can easily reason just in a few lines of code how to make this happen. And then finally, once again, the power of Postgres, the fact that you can combine Postgres extensions. This one of the favorite things about Postgres is that you can do things like geospatial filters where combining Pgvector with PostGIS, you can use an example of, hey, maybe we had a location-based recommendation service that only recommends things to tourists within a 5-kilometer radius. And it's ordered by both your cosine distance in terms of your interests, but also by your geographic distance, so that we don't recommend things that are not relevant to the user or that are very far away, which people don't want to travel all the way too far. Okay. So that is filters. And then finally, pro tip, you'll remember that the pgvector scale extension and the streaming disk-NN index, it actually helps you to get higher search accuracy for filtered search. This is a diagram of how it works, where it exposes this get next function in order to ensure that you will keep looking at the graph in order to get results that match your filter criteria. But the pro tip is, hey, if you have this filtering use case, just use streaming disk-NN, just use pgvector scale. It's going to work better than the other indexes out of the box. Okay, now that we've done filters, let's power through the last few topics before we end off. Hybrid search. So hybrid search, what is hybrid search? This is where you combine vector and keyword search. Once again, the goal is to get more accurate and useful information for the users. And we know earlier you learned that semantic search is search by meaning, but sometimes we do want to search by keyword. So for example, let's say you have a bunch of journal articles or research articles, and you actually want to search by keyword in the title, but then do semantic search, for example, in the abstract or something like that. Or you want to do both searches and combine them and see which one actually has the best results. Essentially, that's what hybrid search is. You're combining vector search with full text and keyword search-based methods. And there's a couple ways to implement this in Postgres. You can combine pgvector and pgvector scale with the native Postgres full text search. This is called tsearch or tsvector. There's Postgres docs about how to do this. There's also further reading that I recommend, including blogs on the Timescale blog and a recent one by Jonathan Katz out of AWS. And this is an example of how we did it using what's called a re-ranker. So this is from a company called 𝗥𝗲𝗃, where basically what we do is we take our documents, we then do a semantic search and a keyword search. So semantic search using 𝗥𝗃𝗃 and keyword search using Postgres. Then both of these are all stored in Postgres. And then what happens is that we get the results from both of these searches, and then we use what's called a re-ranking model to re-rank them, and then finally give the results to the user. So this is just one approach. There's other approaches that you can use. This one is pretty simple, and we've had success with people implementing it before. Hybrid search example, there's a code example that I'll give you in this blog. You can go and read it, called Building Search and RAG Systems on Postgres using 𝗥𝗃𝗃 and pgAI, where we actually implement a hybrid search example just in SQL, all in one query, and it takes you through doing the two searches, re-ranking, all in SQL, all using the pgAI extension. So we'll skip this for now. You'll get the code to look at it later, or you can go and look at this blog post if you're interested. And then the second to last topic that we're going to talk about is multi-tenancy. This is actually pretty important when you're dealing with RAG applications, because a lot of the times you want to have multiple users. You want to ensure that the users, if you're not searching across tenants, let's say you're building a SaaS application or something like that, multi-tenancy is super important to you. If you're not familiar with multi-tenancy, you can think of it like tenants in an apartment building, where, just like you have multiple families in an apartment, you'd have multiple users in different slots in your application. There's different levels you can do this at. I'm not going to read everything in the slide, but basically for certain kinds of applications, you can just give each tenant its own table, where let's say it's like an internal application or something like that. You'd want to give each tenant its own table. It's simple to implement, and you don't have to use multiple databases and stuff like that. But in some cases, it's not great for security. Again, limited data isolation, there's potential for data leaks. What we found works well is giving tenants their own schema. So this kind of works for most cases in terms of balancing isolation and efficiency. So again, you have better data isolation. You can keep everything in the same database. The only con here is that you may hit schema limits if you have like millions of tenants, and it's slightly more complex to set up. Some of the other methods that you can do are things like separating out your tenants by a logical database. So you give them their own logical database. This is more complex to manage. You don't really get that much. You get some like stronger data isolation, but you have a lot more overhead here where you have to have a high backup and maintenance complexity because you'd have to like back up and restore like individual Postgres databases, which can be tricky. And then finally, this is the most expensive approach, but for clients who want the highest level of security, just give them each their own database. And that's possible, especially with infrastructure as code, things like Terraform and stuff like that. You can provision and deploy these pretty easily. Okay, so that's an overview of multi-tenancy. The final thing I'm going to talk about before we end up is text-to-SQL. This is one of my favorite things about Postgres, the fact that you can store structured data, numbers and things in SQL tables, things that have relations, alongside unstructured data. And in terms of AI applications, what that enables you to do is to build a couple of cool use cases. The first one that I wanted to mention is enable your users to query things in structured data, query structured data in natural language. This is a lot of the like chat with your data applications. And then the coolest thing that I wanted to show you guys a demo, but we're not going to have time, is an AI agent with tools to do semantic search and SQL querying, where it can actually decide which tool to use and when. We get into some of this in this blog post. I say read this blog post. It's called RAG is More Than Vector Search. There's a section on implementing text-to-SQL if you're interested. There's sample code, and there's also an associated GitHub repo. Okay, and then this brings us to the end of the webinar. I see folks are enjoying this in the chat. It really means a lot to me. We spend a lot of time on these presentations. My thing is that there's so much of information out there. How can we make this 1 hour really useful to you folks so that you don't feel like, hey, you wasted your time? So again, comments like yours, I really do appreciate it. Our thing is to make sure that people actually learn something and can stop wasting time reading random tutorials and stuff like that. Okay, rant aside, resource is the next step. So what can you do? You learned all the stuff. You're excited. You're energized to build. Here's where you need to direct your attention. To build, go and check out the Pgvector GitHub. Give us a star. Check out the pgAI GitHub. Give us a star there if you like it. This is all, again, once again, open source. There's some documentation. There's some tutorials there. And then I have to, because they pay my salary, if you do want to have a managed database service, you don't want to spend time managing your data infrastructure, but rather want to spend more time building your AI application, check out Timescale Cloud. It's the best Postgres hosting provider out there, especially for AI applications, because it comes with all the extensions that I talked about, pgAI, Pgvector, and Pgvector out of the box, and you can use them straight away. And then for reading, if you want to learn more, there's 2 resources that I recommend. One is this new blog that we just put out called RAG is More Than Vector Search. It'll take you a lot deeper. And then if you want to deep dive into any of the topics that we talked about, go and look at the Timescale blog. There's a lot of tutorials, guides, and explainers for both beginners and intermediate and advanced folks. I hope you learned something in today's session. Have a wonderful rest of your day, and excited to see what AI applications you build with Postgres.